this GFT condensates can effectively reproduce the classical FLRW dynamics. And so in that sense, we said that there is some emergence of space-time.
The easiest thing to do in physics is to take a system you understand and perturb it, introducing slight modifications and studying how they behave. For instance, we can take the electromagnetic field and add some tiny waves here and there, describing their evolution. What happens when you try to follow this route in tackling the problem of quantum gravity?
Actually, I was studying non-perturbative approach to quantum gravity, but this is just a name, and the perturbative method you just mentioned is actually widely used also in non-perturbative quantum gravity models. And to be more precise, I think it will be nice if I take one of my programs as an example. So the quantum gravity formalism I studied is named the group field theory, GFT. And in GFT, we have some tetrahedron as the building block of three-dimensional space. Then we will use this tetrahedron to build some microstate of the space we are interested in. So, of course, the simplest geometry we can think about is the isotropic and the homogeneous space, right? And it's usually related to some universe, for example, the FLRW dynamics. And actually, so far, GFT has successfully somehow reproduced this kind of isotropic dynamics from its construction. And now, of course, we may say that, but the geometry you are talking about is too trivial or too simple to be interesting. And what if we want to some more complicated case? And in this kind of situation, we exactly use the perturbative method you mentioned in this question. So for isotropic space, in GFT, we will use some regular tetrahedron. So all four faces of this kind of tetrahedron are exactly the same. But now we want to some, for example, some anisotropic space. And then what we do is to slightly change the shape of our spatial quanta. So it will, maybe one face will be a little bit smaller or larger, and then we call them some anisotropic perturbation. And then what we do is actually starting from the isotropic construction. And we add this kind of anisotropic perturbation on our original model to see if there is anything new to happen. And luckily is that this kind of construction can largely simplify our computation and also somehow capture some non-trivial feature of anisotropic space. And also, I think there will be some other kind of applications in other approaches to quantum gravity.
Thank you very much. So if I understand correctly, you construct space by gluing some
Yes.
tetrahedra, right? Like
Yes.
regular face,
Right.
then you construct space like with
Yeah, exactly.
okay, with a literal geometric kind of procedure.
Right.
And then
Yes.
your anisotropies, where isotropic for our audience means the same in all directions, right? The same in all directions.
Yes.
You
Right.
use, like you break this isotropy by changing one
Mhm.
face of one tetrahedron here and there and perturbing it that way. Is that correct?
Yes, this is one definition of isotropy in GFT. And we can think about it, maybe imagine that we have a tetrahedron. And in this kind of definition of isotropy, we means like maybe from the some point at the center of this tetrahedron, it will and then it will, let's say, it will see exactly the same thing, no matter which direction we are looking to. And also there can be another kind of definition, and this kind of definition is more widely used in loop quantum cosmology, is that in this kind of definition, maybe we don't use regular tetrahedron, but instead we will use some three orthogonal tetrahedron, like it has three edges and orthogonal among each other. And then we require that the lengths of these edges are the same. So in this kind of definition, the isotropy means that if we start from this point where three edges meeting each other, and they will find exactly the same thing along the direction of the edges.
Okay, so in a sense, you can
Yes.
either formulate it using the faces of the tetrahedron
Yes.
or the edge of
Right.
the tetrahedron. Okay, okay, amazing.
Yes. Right. We have various definitions.
But that's
And but
important.
the essence of perturbation is the same, just like change the shapes or maybe change the lengths of the tetrahedron, and say, okay, now there is something different, and it's a little bit anisotropic.
Okay, okay.
Yes.
So this is how perturbations work. But you start
Right.
by claiming that GFT, or in general, the things you work on, are
Mhm.
non-perturbative approaches to quantum gravity. Can you please
Yes.
tell me something more about what it means? Because our audience might not be used to this word, non-perturbative. We've
Ah.
discussed perturbations. Let's move to non-perturbative. What would you
Right.
consider as a non-perturbative theory of quantum gravity?
Okay, sure. Um, so roughly speaking, we can classify the approaches to quantum gravity into two groups, and one is a perturbative approach, and then here there comes the non-perturbative approaches. And I think a very good example for perturbative approach is the string theory. I think maybe this is the most famous candidate, right? And of course, this is just a very rough classification because actually we know that string also has some non-perturbative uh, descriptions.
Mhm.
But the basic idea of perturbative theory is that we still have some background spacetime and we do some perturbation on it. And this perturbation is usually named as graviton. And I think also there are many people familiar to this concept. But now let's talk about what. So on the opposite, opposite side, we also have non-perturbative approach, and this means that we don't have background space-time. To understand it, we just think about the general relativity again. So what general relativity tells us that is our theory is actually diffeomorphism invariant. And so the theory must be something which independent of background. Therefore, there are some people who are unsatisfied by the perturbative approach. They may say, okay, but I'm not quite happy with your construction because you still have some background spacetime which is not dynamical. So honestly speaking, the non-perturbative theory to quantum gravity is an attempt to get a consistent quantization which strictly obey the diffeomorphism invariance um, required by GR. And also, there may be another difference is that some people may believe that string theory can be a theory of everything or the final theory, but the non-perturbative theory is not so ambitious. And what people trying to do is just simply quantizing the gravity in a background independent way.
Okay, thank you very much. Let me see if I understood what you're saying correctly, and
Yes.
please stop me if my summary is not appropriate. Like, you say that the main difference between perturbative and non-perturbative approaches is that in general relativity, we are told that there should be no background because we have this kind of
Mm,
symmetry which we call diffeomorphism,
yeah,
right?
exactly.
Even start with a space-time, right? We should get it from the theory, right?
Yes, right.
So in a perturbative approach, you take a spacetime and you make little wiggles on it,
Right.
while in a non-perturbative one, you try really not to start with a spacetime from the beginning, right? To get it out from your computer.
Right. That's the idea.
Okay, amazing, amazing, because this allows me to go into one of the interesting features of the general theory of relativity, which is what we are trying to turn into a quantum theory in the end, right?
Right.
That GR somehow tells us that in order to uh, treat space-time physically, you really need
Yeah.
to use rulers and clocks, right? Precisely, it's not a
Yeah.
background structure, right? It's something about rulers
Exactly.
and clocks. And somehow, I would say that in a complete theory of the universe, rulers and clocks should be realized by physical fields, physical objects, right? So is
Yeah.
there a way to achieve this? And how should we understand this attempt to get rulers and clocks in quantum gravity?
Right. Very, very nice question. So here, as I just mentioned, that we don't have background space-time. So at first sight, people may think that then it's impossible because we are not allowed to use any mathematical tools such like maybe background manifold or any coordinate system. And then in non-perturbative approach, we have something called a relational reference frame. And I think this is exactly what you just mentioned, like something we need physical rulers or clocks. And so let me go with more details. And actually, maybe let's just forget about the quantum gravity first. Just simply think about some matter or some field. And of course, in field theory, we can freely use some background spacetime and use coordinates and or parameters to tell us the evolution of a system. And then what we are really doing is actually taking some local value of the gravitational field to describe their dynamics. And this is what a GR tells us, right? And also, there is a very interesting metaphor in Carol Overly's quantum gravity book that maybe I'd like to cite here. Is that so the fields we are dealing with, maybe like some animals, some rabbits or cats, and we just imagine that they are running on some ground or some island. But what Einstein tells us that, oh no, that's not an island. It's a very huge wall, and it's also dynamical. So we so it seems like we are using coordinate system, but we what we are actually doing is to using a dynamical quantity, say the gravitational field, to describe another dynamical quantity. Now let's come back to the quantum gravity and what so here the situation is just actually the same. Like if we can use A to describe B, supposing that they are both dynamical, then why don't we use B to describe A, right? And there comes the idea of relational reference frame. And this means that we will use some physical degrees of freedom. But now, they are not just simply some parameters or just some numbers. We are actually taking their local value and to see how relationally the gravitational field evolves with respect to the value of this matter field. And a good example of it, or maybe the simplest situation that we can consider, is the minimally coupled scalar field. Because we know the scalar field maybe is the simplest field we can think about. And then we can couple it with our maybe some microstates or any system we are interested in. And we assume that they are all dynamical And then we will say, okay, now let's calculate how our system will evolve or will behave with respect to some value of this dynamical field. And then we will call this kind of matter field like rulers or clocks, and depending on how many degrees of freedoms we will have.
Okay, this is amazing. Let me please try to restate it just to
Yes.
make sure our audience understands how radical this is, right? Because on the one hand, you're telling me there's no absolute rulers or clocks like the ones we use in classical mechanics. We get
Yes.
GR.
No.
And on the other,
No.
you suggest to, well, not just you in particular, right? I don't want to put the burden all on your shoulders, but you as a community suggest to substitute them with actual physical fields, perhaps scalars, right? Which are
Yes.
here you could treat them, you can treat properly. The point here would be not to express the quantities we work with in physics, like the values of fields, with respect to some abstract coordinates, but with respect to one another, right? What's the value of
Right.
this field when that other field has this value, and that's it? Is this more or less the idea?
Right. This is what we. This is the axioms of relational reference frame. Um, the, um, so to be more precise, maybe for example, we have some operators to tell us the value of the matter field, and then we do some measurement. We of course we can take some value of it. And then we can also have some other operators, like some geometric quantities, like the areas or the volumes of some state. And we do some, also we can do some measurement on it. And we can say, now we know how this quantity behaves when the matter field take this kind of value. And of course, we won't be able to know how this matter field varies. What we only know is that how our field behaves when this matter field takes some certain values.
Amazing, amazing. So, okay, this is one of the starting points. But you
Yes.
go a bit further because you mentioned the fact that you've been working on group field theories, right? And you told us something about group field theories clearly at the beginning, but I guess it's
Yes.
now time for us to go a bit deeper into the
Mm.
specific features of this approach. What can you tell us about group field theories?
Right. Perhaps for many people, this name is already a very strange thing, right? Some time ago, I received some comments like I know group theory and I also know field theory, but what is group field theory? And so maybe in short, it's it should be a field theory. And I think this is quite a good name because it contains all the essence of this formalism. First of all, as I mentioned, that it's a field theory. This means that it borrows many techniques from quantum field theory, QFT. For example, if we have some GFT actions, we will find that there is also some derivative operators or something else, which looks like something we will meet in QFT. And then, of course, it can also have some path integral formalisms. So it's also a very common techniques in QFT, right? But you may ask, okay, then you already said it's non-perturbative approach. How can you say that it's a field theory? So the main difference is that instead of living on some background spacetime, the field described by GFT is living on a group manifold. And usually we will take this group to be some Lie group. And and this group will tell us the background structure. So, for example, since we are talking about gravity, so maybe we want some Lorentz invariants, right? And in this case, maybe we can use we can choose the group to be Lorentz group. Or if it's too complicated, we can somehow simplify and take some subgroup like SU2 group. And so far, I think SU2 is widely used in GFT because there is another important feature of GFT is that it somehow captured the convergences between various non-perturbative approach to quantum gravity. Now, for example, I think the most well-known candidate of non-perturbative approach is the loop quantum gravity, right? And the full name of it can be the canonical loop quantum gravity, because we believe that it may be the canonical quantization of GR. Then what we know that if there is a canonical quantization, there should be also some covariant quantization. So another formalism named spinfold model, we suppose that it may be the covariant version of quantum gravity. But so far, the relation between these two formalisms are not so clear for us. And then let's come back to GFT. So when we choose the group to be SU2, we can prove that GFT can be viewed as a second quantized version of loop quantum gravity. And on the other hand, the calculation tells us that the group field theory can also reproduce some spin-form amplitude. And so we can see that these non-perturbative formalisms are not completely independent of each other. And these kind of similarities are somehow captured by GFT, and that's why we are interested in it. And maybe so far, I think there are also many works in GFT concerning the quantum cosmology. And now it can, to some extent, reproduce the FLRW dynamics at a continuum limit. Right.
Thank you. So just to see whether I've understood properly, the idea here is that usually when we do field theory or quantum field theory, we define
Yes,
fields on space-time, right? Taking space
exactly.
geometric manifold. Well,
Right.
here, since we don't want space-time to be a background, we take
Exactly.
another object, which is a group manifold, usually a Lie group manifold, you said.
Right.
Groups, for people that might not be familiar with the term, are structures we use to describe symmetries or transformations of physical
Yeah.
objects, which
Right.
also admit a geometric description. So you take this geometric description and define your theory on that. Is this correct?
Right. Exactly. And so in GFT, the variables will be some group elements instead of the coordinate we usually meet in QFT.
Okay, amazing, amazing. And so that way you manage to somehow force the group properties, the symmetries described by the group to be inherited by the theory you get in the end, right? You start with Lorentz group and you get a Lorentz invariant theory, something like that. You start with SU2 and you get something that looks like loop quantum gravity. Is that so?
Yes, exactly.
Okay.
So, right, we have various choices of groups, and it just depends on the systems we are interested in.
Okay, okay, thank you. So you mentioned the cosmology in a way, which is
Right.
absolutely interesting because we live in the universe and we want to know how the universe evolved and came into being and transformed over time. But
Yes.
if you think about the single best known non-perturbative gravitational state, that is gravity, right? So
Exactly.
cosmology aside for a second and try to focus on black holes, which are super pop, work really well. People are super interested in black holes, so we can discuss them.
Yeah.
So joke aside,
Um,
yeah. How does group field theory try to tackle the the problem of quantum black holes?
right. This is also a very important issue, not only for GFT, but also I think all the quantum gravity formalisms try to resolve the black hole singularity, and so of course. GFT also want to tackle the black hole problems, but compared with other approaches, GFT is a very young candidate for quantum gravity. So the black hole project is still at its beginning stage, and so okay, and the basic idea of GFT black hole is to use some strategy called quantum gravity condensates, and right, because we know that it will be very complicated if we have lots of spatial quanta or tetrahedron. And then we do some simplification, is that we use this so-called quantum gravity condensate state to give us a mean field approximation. And the basic idea is like we just treat the tetrahedron um, and use them to define some condensate state in exactly the same way of a coherent state in condensed matter physics. So here, right, we have a condense of spatial quanta, and we will only study the collective degrees of freedom. So it largely simplifies the calculation. And then we assume that the black hole spacetime is also um, something emergent from the quantum gravity condensates, and um, right, and we then what we do is to first of all try defining some candidate microstate of black hole. And what we do next is to do some measurement, just to use the rulers and clocks we just discussed previously, and to see if it can somehow match what we can get from the classical side if we do the same performance. And if they match, then we can say, okay, our state somehow can reproduce the classical black hole spacetime at some continuum limit. And but there are still some limitations of GFT black hole because so far it's still at beginning stage. So we only have very limited techniques, and actually, what we have is still the kinetic description. So this means that we can only tell whether the observables um, behaves well, and even for the observables, actually there is another problem about the curvature, because when we are talking about black hole or singularities, of course the curvature is one of the most important themes, and but the curvature is a very different observables, and so far we don't have a very good construction of curvature operators. This means that we are not able at the time being to measure the curvature of our microstate. So we are not able to say whether we have resolved the curvature singularity in our state. And on the other hand, is that we we don't have the description of the black hole dynamics, and because it's very challenging in computation. But I think if we also apply the perturbative method we discussed at the very beginning, I think we can somehow make our states a little bit more non-trivial, because what we have so far is just a Schwarzschild geometry. I think it's the simplest black hole geometry we can think about. And then to be more physical, I think in the future we need to consider the charged or some rotating black holes, and to tell us whether it can give us anything more interesting.
Thank you. So the general philosophy here is to, group field theory gives you this tetrahedra from which you expect spacetime to emerge. So the most natural thing to do is to take them and do what people do in condensed matter, right? Study their collective
Yes.
behavior. So you somehow take some condensed matter techniques and apply them to a huge number of spacetime tetrahedra. Is that appropriate?
Uh, yeah, exactly. It's like we have really a huge number of building blocks, but so in this way we can somehow do some mean field approximation and see how they behave collectively instead of studying them one by one. So the computation will be much more convenient.
Well, this is philosophically quite challenging because that would imply space-time. And that's really nice, but space-time to be fully emergent from the dynamics of these fundamental degrees of freedom, right?
Right. And so when talking about this quantum gravity condensate, I think perhaps because we don't have dynamics in black hole, um, I think the cosmology will be a better example for it. And actually, right, for the quantum cosmology in the language of GFT, we also use the same technique, this condensed state. And so in that case, because it's isotropic and homogeneous, and then the equations is more more straightforward to compute. And in that way, we can find that when the number of the tetrahedron is infinitely large, then these GFT condensates can effectively reproduce the classical FLRW dynamics. And so, in that sense, we said that there is some emergence of space-time.
Wow. Wow. So with space-time being emergent and with this fascinating, point to which we got, I'd say it's now time to move to a final questions, if you agree. Namely, the more personal one, not private, but personal. So I would start by asking you, because this might be very important for our younger audience, right? How you got interested
Yes.
in this kind of topic, in quantum gravity and then GFT.
It may okay. Um, my interest in quantum gravity is mainly developed by two books. It may seem very crazy, but these two books, one is the Dialogue by Galileo, and the other is the Elegant Universe by Green. I know that the content completely irrelevant to non-perturbative quantum gravity, but I think they share the same spirit, and um, so no matter what kind of topic you are studying, and maybe it's perturbative or maybe it's non-perturbative, um, but the the point is you must rethink about the concept or the definition and even the arguments that you are using so far in order to tackle some problems. And I think not only for researchers in quantum gravity, but also other fundamental subjects. I believe that many people have the same feeling that sometimes you just get stuck, not not because that you are limited by human intelligence, but that there is some misunderstanding of maybe some concepts or maybe some definitions. And I think the relational reference frame we were discussing is a very good example. It's like now we get rid of the background spacetime that we are relying on for such a long time. And um, and I think it's very exciting and also interesting to just challenge yourself and also what you have been believing for such a long time.
Well, that's inspiring in a way. That's inspiring. And on top of being ready to give up on all the concepts and rethink about your prejudices, is there any other advice you would give to young students willing to do research in quantum gravity?
Uh, right. I believe that most of them are very clever, and so perhaps maybe I can hardly give them some useful advice, but I think it will be very helpful for master student and especially for the undergraduate student to first join maybe some research group, because I know that many of these students they get interested in quantum gravity because they read many good books, especially the popular science books, and then I think it's necessary for them to know what's really going on if they want to conduct scientific research. As we know that actually it's quite different from what's written in popular books, and um, and then I think it's also a very good chance for them to get some skills for research or maybe academic writing and to see how the scientific research works. Then I think they will be able to do some more serious decision on whether they should keep going or not. And also, I think it's very necessary if they really want to pursue a career as a researcher in quantum gravity, um, to ask their supervisor for more advice. And right, they will know more details, and because you finally need to get a job, right? Um, and then I would say that after you begin your PhD, I know it will be a very difficult time for you, but I think it's also a very valuable and meaningful experience, and um, people who persist will get reward finally.
And on this optimistic note, I'd say
Right.
it's time for us to depart. Dr. Wang, thank you very much for your time, and I hope to see you soon here.
Okay, and also thank you for your invitation and your excellent questions.
Too kind, too kind. Everyone, and see you soon.
Okay, see you.